Swayam Prabha. Digital India. Educated India.
Hi everyone, welcome again to the course of structural biology. As we are continuing with structural biology techniques and completed X-ray crystallography, today in the new module I am going to teach you NMR spectroscopy, but as we have gone through the detailing of X-ray crystallography in case of NMR spectroscopy, I am not going like that. I am just giving you a basic concept which will help you to understand what is NMR spectroscopy and what is its application, and this will help you to take further interest knowing more about NMR spectroscopy. To start with, NMR spectroscopy or nuclear magnetic resonance spectroscopy is a powerful analytical technique used to characterize organic and biological molecule by identifying carbon hydrogen framework within molecules. So, as the definition says, it is a analytical technique, it is a powerful technique, and it have immense contribution especially for organic chemist and mostly in the entire branch of chemistry, and in case of biology, understanding biological macromolecule, their structure, in polymer and in various other fields. Here we are talking about identifying carbon hydrogen frameworks. I will keep explaining and you understand what I mean here, but from our previous discussions I hope you guys understood now the fact that the world is majorly made of carbon and hydrogen, right. So, this is where NMR spectroscopy play really powerful role in identification. It is a research technique that exploits the magnetic properties of certain atomic nuclei. So, as the name suggests, here we are getting the nucleus correlating to its magnetic property, so that we could identify a particular atom or element. It determines the physical and chemical properties of atoms or the molecules in which they are contained, means it could identify an individual atom or molecules where a group of atoms are there, or even a polymer which is made of repeating units of monomers or combination of different monomers. When I talk about NMR, I never forget the story which I was experienced as a PhD student when I was doing my PhD in University of Illinois, Chicago. So, what happened? There was a presentation from a company who sells NMR instruments, and the first format picture was, there is a NMR machine like that you could see in the screen, and a lot of monkeys surrounded the machine, and they are all just as you see in this picture, very elated, they do not understand anything what is happening type of. And one of our professor just jokingly asked to the speaker, so you think we all are who are listening to you a monkeys, and the speaker representing the company of that NMR instrument replied, sir, with looking at the big era of knowledge you all have, you please pardon me, but when we look at the potential of an NMR instrument, what it could do and how much it is explored, unfortunately we all are monkeys. I think I am explaining little bit, you will understand. When we are doing protein crystallography, we are limited to carbon, nitrogen, oxygen detection. Similarly, if you look at many instrumentation and their related principles, you will see that they have their own limitations with respect to the identification. Whereas, the instrument or the technique nuclear magnetic resonance, it could easily cover the entire periodic table with only one condition: the element or its isotope have to be NMR active. What I mean by NMR active? Let us look at, and let us also look at the general application to start with. So, I talked about that NMR have diverse application, we will keep talking about, but this is the introduction. NMR is a very unique spectroscopic tool, both in terms of its generalized principle as well as its universal use. So, I kind of introducing you why the principle is generalized, because as I told, it could cover the entire periodic table, it is not restricted to few elements to detect, and we will discuss that throughout this 5 class module. But in other side, the application of NMR is also very universal. It has application in a wide area of science and technology. For example, it is applicable in medicine, where it has very popular application called magnetic resonance imaging or MRI, and MRI have real revolution in the world of medical science. NMR spectroscopy is also used in different areas like microscopy, food technology, and in fact testing of many of the food products nowadays in many companies is done using NMR spectroscopy. But the major focus of this course, if I say, will be the basics of the NMR technique and its application towards biological macromolecules. So, how we proceed with, we will start with the generalized application, talking about spectroscopy, going focus to NMR spectroscopy, looking at the principles and techniques majorly used, and then how it is applicable to small molecules, because one of the very critical use of NMR is small molecule. It have revolutionized the place where identification of pure small molecule have performed. So, we will talk about them and then we will go to the biological macromolecule protein. It is a non-invasive and non-destructive method. So, one of the biggest advantage of NMR is it is a non-invasive and a non-destructive method. So, when I say non-invasive, you could understand non-destructive, it does not destruct the sample, but what is non-invasive? In terms of medical science, non-invasive is a medical procedure which is defined when no break in the skin is created and there is no contact with the mucosa or skin break or internal body cavity beyond a natural or artificial body orifice. In one word, when we see a technique is applied to a body part and even no minor injury happened, that is called non-invasive. Non-invasive methodologies are getting popular day by day because of their easy to use, because of their not putting effect especially on chronic diseases like diabetes and all, where every day you have to check and every day you have to put medicine. So, in those sectors non-invasive techniques are really getting popular. NMR is a non-invasive technique, and this means that if you take a sample of your compound, of your molecule and record NMR data on that, you get back to the sample being intact. Nothing happens to the sample, it is not destroyed and could even be reused. In fact, that is why MRI, if you think it is applied to a living organism, you get the whole body scan, you get the brain scan and all these things, and nothing happened to the person on whom the test have been done. So, in fact, in MRI the same thing applies when the whole body imaging is carried out in a non-destructive and a non-invasive manner. So, this being a non-invasive and non-destructive method is unique for NMR comparing to other techniques. The next point is that in NMR spectroscopy you can actually study each and every atom in a given molecule. As we know, molecules are made up of atoms. There are different types of atoms in a given molecule. Almost every atom can be selectively probed or looked at in a very sensitive manner, and this is definitely a very major advantage of NMR spectroscopy compared to other techniques. In other techniques, you look at the whole molecule as such, you do not actually get glimpse of each and every atom in a molecule, but that is where NMR comes in to help us in finding the individualistic structure. So, if I have to explain it, so if you have a compound like a propionic acid, so 4 carbon which is propionic, then 3 carbon, then 2 carbon. Individualistically you could differentiate. Similarly, you could differentiate if there is a hydroxyl group. So, once you do other technique, it is not that they do not identify, they identify the functional groups and all, but this overall identification of each and every atom and their change in the chemical environment, this is the speciality of NMR which we are going to discuss in very details. Also, in NMR spectroscopy you can study the sample or the compound or the molecule which you are interested in under different conditions of pH, temperature, solvent, pressure. So, with different treatment, whatever the effect is coming on the molecule, on the polymer, anything with change of pH, with change of temperature, with different solvent, everything you could get to study using the technique of NMR spectroscopy. Basically, you can actually play around with any condition and keep monitoring the data or acquire the spectra under different conditions. So, this is even interesting. So, in many techniques you treat with something, you make the sample, after sample preparation you go for taking data, you cannot change it, but in case of NMR you could have keep the sample, let us say you have a protein, you keep the protein at 7 pH and then keep increasing the pH and acquire data, or keep decreasing the pH and acquire data. You increase the temperature, you start from 0 degree, you go to different temperature and see what is the effect of the temperature on this protein molecule. So, you not only could take data at various conditions, you could take it in one sample, that is even more helpful. This is a major plus point again, because being a non-destructive technique, as we have already discussed, as long as the sample is valid or not degraded, you can choose any condition and probe the system. So, it is easy to do a lot of condition, lot of variations, more user friendly way than even with some instrument where you could do different conditions, but you have to prepare samples for individual conditions. In addition to that, NMR is also a quantitative technique. So, another prominent advantage is that NMR spectroscopy is a quantitative technique. What is meant by quantitative technique? That means it is actually possible to quantify the percentage of or the amount of some component present in the sample which is under investigation. What do we mean? We mean, suppose there is a solution where there is compounds A, B, C and D. As we have previously talked about, you could have identified them individually in the structural level, you could have see their effect in various conditions, but more interestingly you could also say what is the percentage of the compound A in this sample mixture. So, that is why it is called as a quantitative technique. Since we do not destroy the sample, it is a non-destructive method. You can actually preserve the quantification and measure the amount of particular compound present in the sample. This is very useful in many applications. For example, when we will see later what is called metabolomics. So, NMR metabolomics is something which is very upcoming, and it is a revolution, because you could have even identify components from a very complex mixture of cells. So, we will discuss about that in the application part, where we look at quantity of molecules present in a given mixture. So, this quantitation helping the technique NMR based metabolomics, and nowadays people are actually combining the technique of mass spectrometry with NMR for metabolomics. We would like to know what are the different relative amounts present, and this is where NMR spectroscopy again stands out unique among many other techniques which are comparable. If those are not enough, also NMR is helping us studying dynamics. So, NMR can be used for studying dynamics, and this is very useful because in many different methods such as X-ray crystallography, what happens is you look at the sample in a solid form or you study it in the crystal form, and what you get is only the static structural information, which means a set of coordinates. You are already knowledgeable about X-ray crystallography technique. I have discussed a lot about what is happening in the protein X-ray crystallography. So, you know that we have the crystal, we diffract the crystal and we get the coordinates. We will discuss about the details of the coordinates, but you know that we have the coordinates. So, you have one coordinate, whereas in NMR you are doing at looking the sample in solution. So, you are studying dynamics, and in addition in the solution form the sample is close to the native state where you are doing a lot of other experiments. So, it has all the properties what you would expect to have in its native state, and dynamics is one such important property. Now, when I say about, I would also alert you about something which probably you could misconceptualized in this statement what I made. So, when I say native state, if you remember properly, I have discussed this before. One of the native state is the pure state of a protein, which we call in vitro state. The other one is where it is in the mixture. Mixture means in a cell, in a body, that is called in vivo state. When I say native state, here I mean in vitro state, not the in vivo state. Okay. So, yes, it is not exactly the function of a protein inside a body of a human or body of a, like the body of a mouse, or at least in a cell, it is about the pure protein, but still there is clear advantages over other techniques like crystallography. In crystallography, when you are working, you are putting a lot of precipitants which you call crystallization solution, and you put them because you want to achieve the phase where it is crystallized. So, you push them to precipitate, that we call in crystallostate, and in crystallostate having high concentration of precipitants is very different from in vitro state, and that is where the beauty of NMR technique. So, I hope I could successfully explain it. So, here native state means in vitro state, and as we know that there are many experimental techniques where the experiments are performed in vitro state, it is always advantage to compare them and understand the different properties, which is not possible using the technique of X-ray crystallography. Most of the molecule in solution are very dynamic. They are never static as we see in the pictures. Therefore, understanding dynamics is a very important part of knowing the function of the molecule, and this is where NMR spectroscopy stands out and help us to look at the dynamics at various time scales. So, we have discussed it before. When we have a static structure, it might be a high resolution structure, it might be showing us very intricate details of the atomic interactions, but it is not showing us different conditions, it is not showing us what are the changes happening when it is in solution. That is where NMR is giving us opportunity. We can go from as short as picosecond to as long as few seconds. So, you could have catch those biological phenomena by acquiring data from the solution using the technique of NMR spectroscopy. So, NMR is a spectroscopy technique. So, we want to start with the basic principle of spectroscopy. So, we talk about various application of NMR. Now, we are trying to understand the details of the technique. To start with, we will love to go through first little bit definition of spectroscopy, because we know that in the next module we are continuing with the other low resolution spectroscopy techniques, which are UV vis spectroscopy, circular dichroism, fluorescence spectroscopy, Raman spectroscopy, IR and all. So, this is a continuation. So, we will start understanding spectroscopy. Spectroscopy is about the interaction of light with matter. physicists, chemists and biochemists study how different forms of electromagnetic radiation interact with atoms and molecules. If you see, this is the matter and this is the energy coming, the electromagnetic wave coming, there are different effects. If it is reflect, it is called reflection. If it is go through, it is called transmission. If it is absorbed with the matter, it is called absorption. If it is scattered, it is called scattering. So, interaction of the electromagnetic wave with the matter is not one dimensional. There are many forms of the interaction, many effect of the interaction. And as I say, physicists, chemists and biochemists study how different forms of electromagnetic radiation interact with atoms and molecule, and what are the different effects that would help us to understand or characterize the molecules, if there is any fingerprints, that is what we are looking for. And this interaction we call it spectroscopy. Just as there are various types of electromagnetic radiation, there are various types of spectroscopy depending on the frequency of light we are using, the effect what is showing there and all many different things. So, spectroscopy, by observing such effects and by making analysis of an object's light, astronomers at the starting of where spectroscopy developed can infer the physical properties of that object. They used to see the change of temperature, they used to see the change of mass, they used to see the change of luminosity, and they used to identify the composition, and those early days characterization study later in different form comes to us as different techniques of spectroscopy. In spectroscopy, light rays are a form of energy that can travel through empty space or through some kind of matter. If we see two terms, reflection versus refraction, reflection is other colors bounce of objects and refraction the bending of light rays. Light energy is also called electromagnetic waves. Visible light waves are those we can see, but they are just a small part of the electromagnetic waves produced. Others are radio waves, X-ray, microwaves and many. It does not need matter to move because it could move through the space. When we talk about spectroscopy, this is a good opportunity to talk about human eye, and you will be amazed to see how this technical biological formation have developed. It have lens where the light passes through the clear lens. If you see, this is the lens part, this one. Iris, iris is the color part of the eye, it narrows in bright light and it narrows in darkness. Cornea, cornea is this part where light enters through the cornea and bend light rays. So, this is the cornea part. Retina, retina is an upside down image falls here where cells change light energy to electric and chemical energy in the form of nerve impulses. In biology, you see something, but it is not only a technological seeing. If you see something, your brain have to read that. So, the seeing through eyes should be converted to reading of the brain, which is done by retina. If you see this retina, it change the light energy which is coming to electric and chemical energy in the form of nerve impulses. The nerve goes then and make this message established in the brain. Cornea is convex in front and concave in the back. Retina has a concave surface. So, it is a mixture of lenses made to give the best of the best vision. It is just to talk about, because it seems very relevant with spectroscopy. So, if you see spectroscopy, you will see the prism and white light comes here and they have making dispersion angle, and white light it divided to 7 light rays: red, orange, yellow, green, blue, indigo, violet, where violet is the lowest nanometer containing rays, 400 to 420, indigo 420 to 440, blue 440 to 490, green 490 to 570, yellow is coming in the middle 570 to 585, orange 585 to 620, and red is at the top 620 to 780. The word spectroscopy implies what we will use the electromagnetic spectrum. So, it implies that we will use the electromagnetic spectrum to gain information about the molecule. So, we put the ray, it interact with matter and a lot of changes happens. Looking at those changes, if we could characterize the properties of molecules or anything we want to study, our sample, that is actually called spectroscopy. This is a basic instrumentation of spectroscopy, where you see you have first a light source. We talk about normal light, but it could be different light, also different rays, which we will talk later. Then when the light comes, it would be coming to the wavelength sector. Then there is a shutter would control the light ray to go and hit the sample. After that, there is sample cell where the sample would be kept. Then the effect would be kept in the detector, and finally we will get the readout. So, that is a architecture of a very basic instrumentation of spectroscopy. We will go to different spectroscopy and we will try to discuss the individualistic setup of that instrument. Spectroscopy about electromagnetic radiation. We talked about electromagnetic radiation consists of discrete packets of energy which are called as photons. A photon consists of an oscillating electric field E and an oscillating magnetic field M, which are perpendicular to each other. We also have to talk about few things. Frequency. Frequency is defined as the number of time electric field radiation oscillate in 1 second, that is called frequency. The unit of frequency is hertz. 1 hertz equal to 1 cycle per second. Wavelength. Wavelength is the distance between two nearest parts of the wave in the same phase, that is the distance between two nearest crest or troughs, that is called wavelength. So, if you see, this is the wavelength, that is why it is called lambda, this is the amplitude. The relationship between wavelength and frequency can be written as C equal to nu lambda. As photon is subjected to energy, so E equal to h nu, that means it is replaced by nu lambda. So, nu equal to C by lambda, E equal to h C by lambda. This is called the electromagnetic spectrum, where you see the different rays where they are. So, if you see gamma rays in nanometer, they are 10 to the power minus 4 to 10 to the power minus 2. in centimeter 10 to the power minus 11 to 10 to the power minus 9, in meters 10 to the power minus 13 to 10 to the power minus 11, in between then 10 to the power minus 2 nanometer to 10 nanometer it is X rays, and then 10 to 10 to the power 2 it is UV, 10 to the power 2 to 10 to the power 4 it is visible IR, then from 10 to the power 6 to 10 to the power 7 is microwave, and 10 to the power 7 to 10 to the power 9 is radio. So, these are wavelength, and if you see when we get the wavelengths with increasing wavelength, it is decreasing frequency and decreasing energy. So, gamma rays are around 10 to the power 8 to 10 to the power 6 kilocalorie, whereas radio waves are 10 to the power minus 4 to 10 to the power minus 6 kilocalorie per mole. So, we are focusing on radio wave because in NMR we are using radio wave. Now, you will also understand when I was talking about the invasive non-destructive technique what I mean, because this is about larger wavelength. So, lower frequency and lower energy, because they are lowest energy. So, it explains the non-invasive and non-destructive nature, right, because low energy. So, they do not make any harm to the sample. So, you could keep reusing it. Also, you could apply longer exposure because of the low energy. So, in NMR spectroscopy, the source will basically be a radio wave source. The source of radio wave, as we have seen that NMR relies on radio frequency. So, as we start defining spectroscopy as a study of sample or a molecule or a compound, now every molecule as per our understanding from basic chemistry or physics is made up of atoms. So, every molecule consists of atoms, right. Now, let us take a look at an atom more closely. Atom consists of nucleus, which is at the center of the atom and is surrounded by electron cloud. So, if we go for a basic, this is the nucleus and this is the electrons. This is electrons who are negative charge and nucleus is positive charge, because it have protons and neutrons. Protons are positive, neutrons are neutral. So, overall they are positive. So, that is the basic setup. We could easily see that. Here you could see for the carbon atom 6 electrons are there, 6 neutrons are there and 6 protons are there. So, if we zoom into the nucleus further, we will see the nucleus is made up of protons and neutrons, and we use the word nucleons for both protons and neutrons being together. Neutrons and protons have two properties associated with them, which we will use in NMR. One of the properties is called charge. So, what you know about charge? So, nucleons, it is about neutrons which are neutral, 0 charge, protons they are positive charge. So, overall it is positive. All of us know that protons are positively charged and neutrons have a charge 0, they are neutral. So, overall it is positive. But beside charge, there is one more important property which I am going to introduce, and where NMR is mostly based on is spin. Spin is essentially an abstract quantity, it is a quantum mechanical quantity. Although it is not literally that they are spinning, we can always associate all the properties of angular motion with this quantity called spin. So, it is like the angular motion which is its property. So, I would suggest to keep in mind that it is not literally a rotation which is going on, but at the same time we associate a property called spin which will be very useful here. The spin value of a proton and neutron are same, both are fermions in terms of that and equal to half h by 2 pi, where h is Planck's constant. Now, it is understandable that both protons and neutrons have spin, but the charge is present only for proton, as I told, and neutron does not have a charge, which means the overall nucleus has a positive charge. It is clear for us in the, now. So, this whole positively charged nucleus now has a spin associated with it, because the protons and neutrons inside the nucleus have spins. Now, we will look at pairing up of proton and neutron with each other. So, what happens is that the protons and neutrons are pairing up with each other. Parallel pairing results in addition of the spin values, and anti-parallel pairing essentially cancel out the spin of the particle. So, it would be parallel pairing or it would be anti-parallel pairing. That means the nucleus, after pairing the protons and neutrons together, has a net spin value. The net spin value is the value which you arrive at after pairing up all the protons and neutrons. So, you have the nucleus, let us say carbon, you have 6 neutron, you have 6 proton. So, if you pair up, it would have cancel each other 0. This net spin can have any value, as we will see shortly, and can be determined based on the number of protons and neutrons, or basically based on the atomic mass and atomic number. Okay. Let us see. And also to be remember very honestly and very critically, NMR spectroscopy relies on the nucleus having a net spin value which is not 0. So, if it is 0, that is NMR inactive. If it is non-zero, then it is NMR active. Easy to remember, but very critical to remember. That means, if all the protons and neutrons pairs with each other, then the total spin value of the nucleus will become 0, because the positive spin of a nucleon will cancel with the negative spin of another nucleon. Here they do not have different characters, that is how they are coming, it is important. Therefore, if the net total spin is 0, NMR cannot be carried out on that particular atom or element. So, these atom or elements should have what is called a 0 spin and considered as NMR inactive. Let us now find out the conditions which are important for getting spin not equal to 0 or total spin of nucleus to be equal to half integer or integer, because then they are important or they are critical to be working as NMR active. We could apply NMR technique only on them. For this concept that a nucleus or an element can be studied by NMR, we use the word NMR active. So, we say this particular nucleus is NMR active, or this particular nucleus is not active or NMR inactive. Let us look at how one can actually qualitatively determine whether a particular nucleus can be studied by NMR or cannot be studied. You can see the table here which shows how we can estimate the nucleus spin value. We can have an atom having a even atomic mass or it can have an odd atomic mass. So, there are two things, atomic mass and atomic number. Atomic mass could be even odd, atomic number could be even odd. So, there are four conditions, one is even. So, they are 0 NMR inactive like 12C like 16O oxygen, even odd. So, this is even or EE, then OE, half integer 1 by 2, 3 by 2, 5 by 2, 13C is 1 by 2, 17O is 5 by 2. Then we will go for EO, even odd, integral values 2H equal to 1, 14N equal to 1. Then we go for OO, half integer 1 H equal to half, 15 N equal to half. So, we have four conditions E, O, E, O, 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 okay, and this is how we could determine the NMR active or NMR inactive elements. Similarly, the atomic number of that atom can be either even or odd depending on the number of protons. The number of protons decide whether the atomic number is even or odd, and the total number of nucleons, that is proton plus neutron, determine whether the atomic mass is even or odd. This is a very basic concept which you learn in chemistry and physics if you have basic idea about the atom and atomic numbers. We will go through few examples. Let us say we take a particular nucleus carbon 12. It has 6 protons and 6 neutrons. This is an element with even atomic number and even atomic mass, and therefore, the total spin of its nucleus have to be 0, very confidently 0. This means all the protons and neutrons pair with each other and the total net value of the spin for that nucleus becomes equal to 0. Therefore, we cannot study carbon 12 by NMR. Similarly, oxygen 16 has 8 proton and 8 neutrons. It also belongs to this even category, and therefore, it cannot be studied by NMR. Let us look at an example where you have odd atomic number and even atomic mass. This is the case, for example, in deuterium, which is an isotope of hydrogen. Another case is nitrogen 14. Nitrogen 14 has 7 protons, 7 neutrons. It has an even atomic mass, but atomic number is odd here. For such type of an element, atom or a nucleus, we will have integral value of spin. The spin will be integer multiple of 1, 1, 2 like this. The last case is essentially an odd atomic number, odd mass combination. For example, the most popular nucleus in this category is proton. There are no neutrons in a hydrogen atom, hence it is called proton. The nucleus has therefore odd atomic number and also odd atomic weight, mass, and that is why its spin is half integer. A very another important nucleus in this category is N15, isotope of nitrogen, which has 7 protons and 8 neutrons. It also has an odd atomic number, odd atomic mass combination, and hence its spin value is half integer. Now, we have discussed the different conditions by which we can study the different NMR properties, right. Most exciting part of this is one can actually extend this idea to the entire periodic table. Now, if you look at this figure in the periodic table, it is quite clear that many elements in the periodic table can be studied by NMR spectroscopy, because they are having non-zero nuclear spin. You see the nuclear spins half, 1, 3 by 2, 5 by 2, 7 by 2, 9 by 2, all are having different color codes, which you could see here. Now, I could again once talk about the concept of this NMR and monkey. You could see this periodic table, look at the huge potential, and you could feel for 1 minute that with the potential of NMR technique or the generalized versatile principle of NMR, we are in true sense remaining monkey to explore it. And if only the presence or covering the periodic table is not enough, I will talk about the isotopes. What is about isotopes? As you will remember, I told that C12 is completely NMR inactive, but not C13. C13 is an isotope of carbon which is very less abundant in nature, but it is NMR active. So, in summary, either the compound, the element itself can be studied in the natural abundance, but it is also possible to study its isotope which might be less abundant naturally. So, we are talking about abundance. What is abundance? Abundance is something which will be very critical for choosing an element or its isotope in the study of NMR. Abundance basically means that in a given natural state, what is the percentage of a given isotope of the element which is present in that molecule. We will talk with examples. For example, the natural abundance of carbon 12 is 99%. This implies 99% of the carbon atom in the sample have carbon 12. The remaining 1% is mainly carbon 13, as for the NMR is considered only this 1% 13C which is present contributes to the signal in the technique of NMR spectroscopy. The remaining 99% does not, it is just blind or transparent to NMR because it has 0 spin. You can see that the sensitivity of 13C becomes low because on an average out of 100 carbon atoms only 1 atom will be C13. Because of that, when you are using carbon to study NMR, you get very low intensity signal because of the less presence of the C13, and that is called abundance. Whereas, as I told, when we consider 1H, it represents 90% as and is NMR active. So, the most common nuclei is proton because of its availability and natural abundance. Typically 90% of NMR is carried out with protons. The second most popular nucleus is 13C, followed by 19F. Fluorine is coming as very important probe. Phosphorus 31, N15 is also very popular nucleus, especially when we study biological macromolecules protein. Fluorine is a very popular in drug industry for investigating pharmaceutical drug. Many of the pharmaceutical drugs have fluorine, and 19F is also very close to 1H in terms of sensitivity. Silicon is used for studying material. So, if you see 1H, 13C, 31P, 15N, 19F and 21 silicon, they are specially used, and all of these have spin equal to half. For such nuclei, many of the NMR phenomena can be easily understood and explained. People generally focus majorly on this particular type of nuclei for their experiments. So, I have started introducing NMR spectroscopy. I talked about the very unique applications of NMR, and it having very versatile principle which help this technique to include most of the members of the periodic table, if not the main isotope, their less abundant isotopes, you could get NMR active signal from nearly every element. So, it is extremely helpful in identification, it have very easy to use principle, and then we will look at how this is going to develop principles where we would be able to work on some compounds, what are the principles, how the instrumentation works, which are the important part of instrumentation, and many things else in next class. Thank you very much.